All right. Thank you for attending my talk. I'm Mazen Saghir with the American University of Beirut. And today I'm going to present the work of my students, Omar Mardini and Omar Shibli, who worked on a systolic array accelerator for TinyML workloads, and they implemented it in CFU Playground. So before we start, just a quick overview of systolic arrays. What are systolic arrays? They're basically two-dimensional processing elements that compute and pass data in a pipeline fashion, and they're really ideal for linear algebra applications like matrix multiplication, which, as we all know, are at the heart of machine learning inference. The main advantage of systolic arrays compared to other accelerators is that they really require very little bandwidth in terms of memory. So there's very minimal data transfer back and forth between main memory, and they can reuse their intermediate results in order to compare or to calculate the final result. And this, of course, reduces energy as well as improves the latency, and this makes them ideal for low-power applications. The simple and regular structures also make them easy to map to FPGAs and ASICs if needed. And this enables real-time inference for small machine learning models like keyword spotting or sensor classification. CFU Playground is an open source framework for rapid prototyping and testing of custom accelerators. CFUs stand for custom functional units, and they're intended to run on RISC-V CPUs aimed at optimizing TinyML workloads. CFU Playground co-simulates, so it has a C++ model, and it allows also a Verilog model to be running on the FPGA, and this enables fast exploration of hardware-software trade-offs. It uses a 32-bit VEX RISC-V host, as well as a synchronous handshaking point-to-point CFU interface. It also uses custom instructions, which it decodes, and this allows it to implement the various functionalities and pass operands to the CFU. CFUs can handle single cycle or single cycle latencies as well as multi-cycle latencies. Here's a block diagram of the system that we developed. On the left is the CPU, and on the right is the CFU, which contains our systolic array. Between the two, there's a ping-pong buffer, so while we are loading data, we should be able to also process data. This is not completely implemented yet. It's still a work in progress. So in today's demo, I'll just show loading data from a file. But the systolic array is working. So we can load the rows and the columns and then have the CFU run. This is running at 100 megahertz, both the CPU as well as the systolic array. This is just showing us in software how do we implement matrix multiplication. This is fairly standard. And this is showing us how we replace the innermost loop by a call to the CFU operation. Okay, here are some of our performance results. So we tried two different array sizes, 3 by 3 and 10 by 10. So for 3 by 3, we see a speed up of about 5 times, and for 10 by 10, we see a speed up of about 10 times. But the main advantage really is in energy consumption. So for the 3 by 3, if we calculate the energy consumed, which we basically do by getting the power consumption from the synthesis reports and multiplying it by the execution time, we see that the 3 by 3 systolic array achieves a savings of about 80% energy consumption compared to the software model. And the 10 by 10 array also achieves about 90% reduction in energy. And at the bottom table, we can see the processor, the resource utilization in terms of lookup tables, as well as DSP blocks. Okay, so with that, I'll just move to the demo. So hopefully my cable will not give me problems, because it was giving me some problems earlier. Let's try again.
We need a new cable.
It's a micro USB, so I'm not sure that it's.
Does anybody have a micro USB?
I apologize for that.
It's an outdated standard.
Yes, it's an old board, so I apologize for that.
There we have one. Looks
Yes,
good.
it is. But I think it's more the connector. But anyways, thank you. Let me try this.
What I can help you with this.
Yep. Let's try.
But do you have a double make there?
Sorry?
You have make.
Oh, sorry. Yeah, thank you.
Can I get the next speaker in line already? Thank you.
Okay, we'll give it one shot.
Oh, it looks good, doesn't it? No?
Let's see if this works.
I think we can Let's wait until.
Yeah, just take a couple of minutes. It's rebuilding. I apologize for that.
Maybe also here, can we? Do you want to rebuild test? Maybe.
Sure. I apologize for that. Basically,
This is the beauty of live demos.
All right. I was just going to run and show you the cycle counts. So,
Yeah. No, maybe
yeah,
we can, conclude.
Sure.
At the end. Okay, then we have 2 minutes.
This is a demo, and we have to show them.
Yeah, we have to show the demo. Yes, exactly.
I was very fast in my talk, I think.
Wait.
Well, the first data are coming out, and my colleague promised to me that more data will come. And the software finished. The connection is lost.
Ooh.
Wow. Come on, the connection with the computer at the university has been lost.
Is the final speaker here as well?
We are still in time.
We are in time, yeah.
Yeah.
Just a final
Consume
speaker.
only 6 minutes.
I think you might get 10 minutes if the final speaker is not not coming. Oh, a lot of data now.
Well, the data are coming, and the final results in terms of instructions executed and.
Can you remind us again? It was a filtering application, or what was running? What is running? What's the application that's
the
running?
noise cancellation filter.
Noise cancellation. Okay, so what do we see here? Is
The data.
the
coming
data?
out.
Yeah.
Yeah.
What data?
The data coming out from the filter.
Okay, so the filtered audio.
Exactly.
Perfect.
Is audio? Yeah.
Yes.
Sure. Yeah, there can be noise everywhere.
Well, in the meantime, I can finish my talk.
I know you're getting brave.
Just to conclude.
Can you just confirm that the final speaker isn't here? Thomas? So, good. Good for you. But we also need to give you... Do you... Okay. Don't worry. It's life.
Okay, just to conclude, the comparison with Spike, which is much faster, and the comparison with Gen 5 in the same conditions. Okay, no hardware, no input-output, data memory, etc. And Gen 5 has a speed of 0.1, which is faster than RTL. Okay, then the idea is that the tool pretends to accelerate the software simulation on an RTL hardware platform. X-Heap is clear that it's not the best example because the size of the processor compared with the size of the complete platform is smaller. This tool will be better performed when the complexity of the computing platform is higher, and in addition to the compared with the rest of the peripherals. And in any case, we expect to achieve higher speed than much higher speed than RTL, providing this at the same time this quasi-cycle accuracy. Okay. And then Spike RTL keeps the instruction execution correctness and can be used to verify not only the functionality but also the performance. Thank you, and sorry for this synchrony between the tool and my talk, and just to see the final results. The final data of the simulation with the simulation results that the tool provides to you. Nice finish, isn't it? Yes. Okay, thank you.